premise. I was going to ask you about that.
Okay, well, we have this. What's our premise? Y some multiple of e to the lambda t, right?
Yes.
And this leads to characteristic equation in a very straightforward manner. And we get lambda squared plus 5 lambda minus 7 equals 0, so that lambda equals -5 plus or minus the square root of 49 minus 20 divided by 2. Right? And it's minus 28. And it's not 49, it's 25.
There we go.
See? Okay? So that's -5 plus or minus the square root of -3 over 2, which is -5 halves plus or minus, yeah, my minus isn't supposed to be a 2, okay? I'm looking ahead to the square root or something. I don't know what my excuse is. So square root of 3 over 2i, right?
Yes.
Okay? So y equals some multiple of e to the -5 halves t, right?
Yes.
E to the square root of 3 halves I t. So we'll call that y1. That's one of our possible solutions. And we don't need the a here because our y1 and y2 are going to be our fundamental set. We're going to do linear combination. We didn't really need the a here, but you know, we proved that by doing the substitution, doing the derivatives and stuff, and the a's all divide out of the equation, right? So, okay, anyhow, we get y2 then equals e to the -5 halves t, e to the negative square root of 3 halves I t. Okay?
Right.
And that means what? That this is e to the -5 halves t times cosine the square root of 3 over 2, square root of 3, have no control over what I write, over 2t plus I sine of the square root of 3 over 2t. And y2 is e to the -5 halves t times the cosine of square root of 3 over 2t minus I sine of square root of 3 over 2t. And the key is the plus and the minus on the sign, which allows us with complex coefficients to get any linear combination of the cosine and the sine here. Okay? And I'm not going to go through the details of that because we've been through them many times. We're just going to say, okay, so without saying too much, I said any linear combination, sine and cosine, right? Okay? So I'm going to write that as C1 cosine of the square root of 3 over 2t plus C2 sine square root of 3 over 2t times e to the -5 halves t. Now the dots we've filled in many times. Again, a general linear combination would be the linear combination you get where C1 and C2, where you use constants on these, and they're complex constants. So you can manipulate the real and imaginary parts of those constants to get any real combination of the sine and cosine or any imaginary combination of the sine and cosine. Now C1 and C2 can still be regarded as complex constants, which is why I don't write the i's here. Then there's some details of that I'm not going to review right now. You can go back and see how we did it, just because we don't have a lot of time. So, you know, it's kind of another premise conclusion and some dots that need to be filled in, okay? But it comes down to this. Okay? Now, if you confine yourself to real constants, then this can be just written as like a cosine of square root of 3 over 2 plus phi, right? And that would be the general solution, because the general solution would have imaginary parts, and that doesn't. Unless, of course, A could be a complex constant, right? And then, you know, there's still some complications you have to get past. But if real, that means if we have just real constants, then you can put this into this form with your phase relationships and so forth.